Hey everyone, and welcome. Sound seems pretty simple, right? But it actually follows some incredibly cool predictable rules as it moves through the world. Today, we're going to pull back the curtain on the secret life of sound waves, and we'll start with a question I bet you've asked yourself before. You know that sound, right? That high-pitched wee-wee as it's coming towards you, and then it suddenly drops to that low woo as it passes by? Well, that's not just in your head, and the driver isn't messing with the siren. That's pure physics in action, and by the end of this, you'll know exactly why it happens. So, first things first, we gotta understand what happens when two sound waves try to be in the same place at the same time. Think about dropping two pebbles into a still pond. The ripples don't just crash and stop, they pass right through each other. And where they overlap, they create this whole new complex pattern. Well, sound waves do the exact same thing.
And this whole interaction has a name. It's called interference. It's all about a concept called superposition. Basically, it just means that wherever waves overlap, you just add their effects together. They can either team up and get stronger, or they can work against each other and get weaker. So what really matters is how they line up. When the peak of one wave, its crest, meets the crest of another, we say they're in phase. They literally build on each other, making a much bigger wave. That's constructive interference, and what we hear is a louder sound. But what if the crest of one wave meets the valley, or trough, of another? Now they're out of phase. They completely cancel each other out, giving you a weaker sound, or, in a perfect world, total silence. And that's destructive interference.
Now, this slide gets into the weeds a bit, but don't worry about the formulas. The big idea here is something called path difference. It's just the difference in how far each wave had to travel to get to your ear. If that difference makes the waves arrive perfectly in step, kind of like two people marching together, you get that loud, constructive interference. But if the path difference makes them arrive completely out of step, one is up while the other is down, you get that quiet, destructive interference. It really all just comes down to timing.
Okay, so that's what happens when identical waves run into each other. But what if they're not quite identical? What if you have two sounds that have slightly different frequencies? Well, this is where things get really interesting and kind of rhythmic.
This effect is called beats. If you've ever heard two musical notes that are almost, but not quite, in tune, you know this sound. It's that pulsing wah, wah, wah you can hear. That's not a new sound being created, that's just the sound of interference happening over and over again in a really regular pattern. And this image shows exactly what's going on. Just focus on the shapes of the waves. See the top two? Their frequencies are just a little bit different. And because of that, they're constantly drifting in and out of sync with each other. For a split second, their crests line up perfectly. That's constructive interference, and the sound gets loud. But then, a moment later, they're totally misaligned, causing destructive interference, and the sound gets quiet. This cycle of loud, quiet, creates that pulsating wave you see at the bottom. That rise and fall in loudness is the beat.
And this isn't just some abstract physics concept, it's an incredibly practical tool. Musicians use this all the time. When a guitarist is tuning their guitar, they'll play a reference note, then play the string they're tuning. They're listening for that wah-wah beat. As they tighten or loosen the string, that beat gets slower, and when it vanishes completely, they know the frequencies match. They are perfectly in tune.
You can even use this as a super precise measurement tool. It's like a little logic puzzle. Let's break this down. Step 1, you've got a tuning fork you know is 256 Hz. And another one that's a mystery. Together you hear 6 beats per second. Right away, that tells you the unknown fork is either 6 Hz lower or 6 Hz higher. So 250 or 262. Step 2, you add a tiny speck of wax to your known fork. This always lowers its frequency a bit. Step 3, now when you play them, you only hear 4 beats per second. The beat got slower. Steps 4 and 5. Okay, so since the beat frequency went down, that means the two frequencies got closer together. And since we know we lowered our 256 Hz fork, the only way they could get closer is if it was moving down toward 250. So the unknown fork has to be 250 Hz. Pretty clever, right? All right, we've talked about waves meeting each other. Now let's throw one more thing into the mix, motion. And this is going to bring us right back to our ambulance siren and the famous Doppler effect. The absolute key word here is apparent. It's an apparent change in frequency. The siren itself isn't actually changing its tune. The change we hear is created entirely by the relative motion between the thing making the sound and the person hearing it. Let's start with the simple case. If nothing's moving, you're standing still, the sound source is standing still, the sound waves spread out in these perfect, evenly spaced circles. The distance between each wave peak is consistent. So the frequency you hear is exactly the frequency being produced. No surprises there.
But as soon as something moves, things change. Check out the image on the left. If the source is still but you run towards it, you're going to run into each sound wave a little more often, right? Your brain hears that as a higher pitch. Now look at the right. If you stand still and the sound source moves towards you, it starts to catch up with its own sound waves, squishing them together out in front. This makes the waves themselves shorter, which also results in a higher frequency. So, two different reasons, but you get the exact same effect, a higher pitch.
This quote just nails it. The waves get all bunched up and crowded in the direction the source is moving. That means a higher pitch for anyone in front of it. And behind it, the waves get stretched out. They spread out. That means a longer wavelength and a lower pitch for anyone listening from behind. This is exactly what's happening with that ambulance. As it races towards you, the waves are compressed, high pitch. The second it passes you, you're suddenly hearing the waves that are being stretched out behind it, low pitch. Mystery solved.
So let's bring it all together. We've got interference, beats, and the Doppler effect. Now, these might sound like they belong in a physics textbook, but they're actually fundamental rules for how all waves behave. And their applications are everywhere, from things we use every day to things that are literally cosmic. Just think about it for a second. Your noise-canceling headphones? They're creating an anti-noise wave to cause destructive interference and give you silence. We already saw how musicians use beats to tune up. Police radar guns and the Doppler radar that meteorologists use to track storms, that's the Doppler effect in action. And maybe coolest of all, astronomers use this same principle with light. By measuring something called redshift, which is just the Doppler effect for light waves coming from distant galaxies, we get the best evidence we have that our entire universe is expanding. It's incredible.
So from a simple ambulance siren all the way to the expansion of the cosmos, these simple, fundamental rules of waves give us these incredibly powerful tools to understand and even manipulate the world around us. It all just starts with knowing how waves can add up, cancel out, and shift with motion. And that makes you wonder, what else can these simple rules explain?